I think we are ready to start. So welcome to our last innovation sessions that we focus on chipsets. So we had a lively main stage panel this morning, and we are lucky to continue the discussion today. My name is Olli Andersson. I will be your moderator today. We have an excellent participation at this session. So we have 90 minutes to discuss what chipsets, different chipset architectures, what technically, what different type of alternatives we have and how important they are for RAN and for communications in general. So today we'll start off with three presentations to dive a little bit more deeper to the chipset evolution and technology. So we'll hear from Qualcomm, we will hear from Vodafone and their silicon research, and then we will hear some new sustainable innovations from ARM, and then we'll actually end up with a lively panel. We have 6 persons in a panel discussion today, and then I hope to, at the end, also to take maybe 1 or 2 questions from the audience as well. So without further ado, I would like to invite Dino Flore from Qualcomm to the stage, and Dino will give a Qualcomm keynote.
Good afternoon, everybody. I guess some of you have already attended the panel this morning, so there was a nice introduction to what I'm going to present. So I'm going to give you a brief overview of the Qualcomm infrastructure solutions and what we're planning, how we're planning to contribute to this transition to ORAN and vRAN. So what we want to do is advancing ORAN ecosystem with peak performance infrastructure solution with lowest energy consumption. So I think energy consumption is becoming more and more important, and I think we have solutions that address that problem. And again, it's a sort of what we were discussing this morning. I will have some data points for you to locate that discussion. So first of all, I was mentioning earlier this morning, so we are contributing to the vRAN ecosystem with a portfolio of solutions. It's a host of solution SoCs, but also a tool for network management as well, the edgewise platform. But today I'm going to focus on the SoCs. So we have a host of SoCs and an accelerator card for the baseband. We'll focus on those today and on what they bring to the table for the ORAN. So first is a reminder how network energy efficient is very important for operators. Today we was mentioned multiple times how it impacts the operators' bills and why is it important. We believe that with ORAN and with restructuring, with the disruption we can create in the infrastructure side, we can definitely reduce power consumption on networks and therefore operator bills. So we have been focusing on a lot of that. And this has a lot to do on the discussion we were having this morning around what is the best computing architecture, what is the best radio architecture to drive down the energy. So this is the solution we have put in the market for the baseband unit, in particular the ODU. And it's an acceleration card, and it's an inline accelerator. But inline here means what we were discussing this morning. So we are offloading from the CPU all the layer 1 processing, all the heavy L1 processing, and all the L1 processing has been moved to an accelerator card. Because of that, and again, back to the discussion this morning, we have proven with tests that we can reduce the energy consumption dramatically compared to the approach, which again, some they make it all look aside, but is an obsolete terminology we said this morning. But again, compared to the approach where you only offload to the accelerator some selected function like forward error correcting capabilities. So again, we've tested this with our partner HPE in some standard configuration, and again, it's just to demonstrate that the computing approach we have been taking it's the one with the lowest energy consumption. And it's important to notice that in terms of KPI, we are able to serve 24 gigabit per second in 40 watt power. That is, to our knowledge, is kind of unmatched in the industry. Also, as I mentioned this morning, so we are not stopping at the radio unit, at the baseband. We are also working on how to optimize the radio unit and on a solution, an SoC for the radio unit. Actually, the radio unit is probably more important. So there is a lot of discussion for some reason on the baseband, the DDU, but at the end of the day, most of the bill for the operator, both for CapEx and OpEx energy consumption, will come from the radio unit, actually. For the radio unit, also, thanks to our leading edge node capabilities, thanks to the integration capabilities we have, so we are able to create solutions which perform much better in terms of, again, power consumption as well. So we have, again, here, we have benchmarked our performance compared to one of the tier one competitors, and we can do much better, again, in power. And radio unit, again, is very, very important, as I said, in the budget of an operator, both CapEx and OpEx. It's important, we were saying this morning, that we work to have an ecosystem around the solution. We are working with multiple partners, operators, and vendors, because we want to create an ecosystem around our platforms and to contribute to the successful of ORAN. Recently, we have announced some special partnership. In this case, we have demonstrated a setup with the Mavenir DU and the OpenBeam radio unit. This has been recently demonstrated, and this is what has been used for also the benchmarks, the performance benchmarks I mentioned before. Also recently, we have started a new collaboration with another promising vendor, Vietel, and I think in this case, working both on the radio unit and the baseband, the DU. So also to show that what we can contribute also to the industry, it's also, this was important, I wanted to stress this in closing, that what we contribute to the industry is also create some diversity in the infrastructure, in infrastructure space, bringing up new vendors, because we can make it easier for new vendors to come to the party and contribute to the ecosystem. And that is what I wanted to show you today. Thank you.
Thank you, Dino. And Dino actually has to leave for an airplane, so we were lucky to have him for a few minutes. So, next, I would like to invite Vaifro Dariol from Vodafone, Malaga. So, Vaifro, please.
Yeah, good afternoon. It's always the first time. Sorry, so I may not be fluid on I'm not used to this attention to so many people at the same time. But so let's start. I feel the need to explain why an operator is sitting on the discussion panel rather than just moderating like my boss was doing this morning. So I need to explain you who we are. So we are an innovation research center in Malaga. We are part of the Vodafone, and our primary focus are on innovation and research for chipset and the research and development for RIC algorithms. We are currently 18, but we will be 50 by 2025. We are running on European funds, and we believe on digital sovereignty. So basically, Vodafone realized that we cannot be any more passive. We need to be active in the ecosystem, and we want to have to build back the knowledge, the deep knowledge that is needed for this change due to ORAN. We are already working with 20 partners, and that are different level. The last couple of days we announced some partnership with Intel, and that was announced on Monday, and with also with ARM. So basically, we are actively partnership with the real player on this. Not that we are not, but as I said, we are located in Malaga. We recently opened our innovation hub. It's quite a nice setting. Whoever want to come, you are more than welcome. There are also some beaches. You know, it's not at all a bad environment. And honestly, I've been punished by Vodafone. They have been sent to Malaga. Somebody has to do it, and so. Why I'm here? I'm here to give our sort of vision that sometimes is not even contaminated by an history, because our group is mainly formed by people coming from other industries. So we are not telecom born, so we don't have the legacy of we have always done like this. So we may have a different vision just because we don't know the market, we don't know, we are ignorant if you want. What we want is that new technologies are taken into consideration. So, for example, photonics. I will describe a bit better later what photonics can bring in the ecosystem. But yeah, we sort of trying to shake the establishment, say, no, we need to bring new ideas, new technology into the ecosystem. Then we have a dream. We dream a reconfigurable processor, something that is neither inline or look aside, the big discussion, is something that can be configured according to the need of the software. So basically runtime, of course. So is at the need of not only telecom, but also other business, actually. This is to revert one of the first paradigm of ORAN, because ORAN, one of the first statement was reduce cost by using off-the-shelf devices. We should reverse that and say, okay, let's create devices that can be off-the-shelf for other market, where the numbers are bigger. And so is where we may get saving by selling what we develop to other market. We dream a DU in a chip. We will work on working group 6, so please all support us on this, even if you don't believe, but on common architecture for the hardware and software interoperability. So there will be a proposal that will include also a reprogrammable microprocessor or microcontroller, or how you want to call it. Let's go more in details about photonics and why I'm speaking about photonics. So let's first look at what the telecommunication world, but not only the telecommunication world, need. So these are taken from OpenAI. The need for machine learning requirement. Machine learning is not 100% correlated to telecom, because there is nothing to learn on an FFT or a turbo coder. Those are, I mean, there is no much margin of improvement there, but we see that beamforming, channel estimation will be needing a lot of machine learning. So if we display this because to show that we may be facing processing requirement that we don't consider now. So this is the current progression on computing requirement, and this is the current processor capability. So on the right is what we need. On the left is what we can get from the evolution. Basically, it's the Moore law that is getting, sadly, in here where we lost him, is topping up. So we think that it's time to jump, and we think that the photonic can make the line increase again. So that's why we are promoting this technology, and we hope that will be used by the silicon producer in the more or less near future. Thank you very much.
All right, so thank you, Vaifro, for representing at least an operator view, if not collective view, but and giving us a glimpse of your needs for the future. At this phase, I would like to welcome Mo Jabbari from ARM, and we are lucky to have ARM as a sponsor for this session. So thank you so much, and Mo, please come to the stage.
Okay, thank you very much. This is way more than we expected. This is the last, or the one before the last session. But I think the morning was so heated that everyone wanted to see what would be the second take. We have Joel here, so it will be fun, possibly. I'll start a little bit about ARM. I assume everybody knows, but 70% of world population is using ARM, one way or another. Just since 2013, we've shipped 50 billion chips. So that's 6 or 7 chips per person. So it's way more than even I expected before joining ARM. It's ubiquitous compute. But everybody knows ARM for cell phones. 99% of maybe cell phone market is using ARM chips. But we are in other markets too. The IoTs, the sensors is a quite natural fit. No sensor can handle battery drain. There is automotive, a rising market, and the cloud and networking infrastructure, which is the segment that I am part of that. This includes cloud providers like AWS, which is well known for support of ARM, and others that are announced or will be announced, and also networking. ARM has always been part of the networking equipment way before vRAN and OpenRAN came along, and still we play a big role in that. Let's call it purpose-built RAN. Now we are in the vRAN times, and we still think the same values that made ARM a perfect choice for classic RAN or purpose-built RAN applies to the OpenRAN and vRAN market. So where is the 5G going? Per a lot of estimates, there will be more and more 5G connections. This is something like 5 billion more connections that is coming to 5G. The rate that 5G is being taken up is much faster than what happened to 3G or 4G across the world. The base stations are becoming more and more power hungry because there is bigger spectrums, there's massive MIMO, the base stations are consuming more and more power. And energy consumption is becoming a bigger chunk of operator energy, operator cost, OpEx, up to 40%, 20 to 40%, depending on what kind of network you are running. And this is, and with rising energy costs and all the geopolitics that you are well aware, this makes attention to power efficiency more and more important in this market. So the drivers for this next generation are a few things. As discussed, the 5G RAN consumes a little bit or significantly more power. So compute efficiency is one of the focuses. There is also the ecosystem support. We are technically looking at opening up this market to more and more partners, more and more companies, create more competition, and that's the whole Open RAN mantra, to create, to break the market into smaller pieces, create an ecosystem there. And finally, the cloudification is the main driver. Separation of hardware from software where it makes sense, and create, bring all the values that cloudification, virtualization brought to the cloud. Now we want to do that for the telcos. One trend we see, which will show all this, at 4G times, there was a lot of focus on accelerators, DSPs for the telco. And there was some level of ARM support, core CPU support, mostly for the control plane on x86. But now that there is more need for compute, there is efficiency requirements, the game is a bit changing. There is still accelerators, you can get away from having the right blend of accelerators, but the role of the CPU cores are increasing more and more in the chipsets. Stronger chipsets, stronger cores are needed, but without compromising on the power efficiency. And that's where we see a good role for ARM, and it's being picked up by the leaders of the market to create the right combination of a chip that has correct general purpose CPUs, which is ARM, and accelerators, DSPs, or whatever that you need on that front. And the gains are substantial. So a few pointers on what has been seen by markets in when technologies of ARM are used in various sections of the market. One of them is, this was announced last year, the NTT Docomo commissioned NEC, which is their core network provider, to do a POC on moving their core network from traditional compute they had, an x86 based solution, to AWS chipsets that are Graviton 2 and 3. These are based on ARM technology. And based on their own measurements, they saw 72% reduction in the power consumption. This work has continued. You will hear more about it in future. There is also strong support from Nokia. As everybody knows, they have chosen Marvell for the chipsets. Marvell chips use as part of their solution ARM Neoverse cores, and the power efficiency of Neoverse cores has been always very appealing for Nokia. That was part of the reason they chose Marvell, except beside everything else that Marvell brings to the table, all the expertise and the right acceleration. Finally, this was a recent announcement SoftBank made with NVIDIA for the vision of centralized RAN, which is something that is coming to fruition, especially in East Asia, where the market, the networks matches a centralized RAN vision. They have started looking at this as mini data centers based on the NVIDIA's mix of CPU and GPU that can not only do vRAN, do more cloud services, technically as a way for operator to break the cycle of being just a pipeline, being able to provide services above vRAN. This might be generative AIs and all these functions that are being seen as the value added on top of the vRAN. So there is this activity. I couldn't put this, to this morning there was an announcement from Vodafone. There was a press release that with one of the ARM ecosystem players, SinaXG, which is actually based on Marvell chips, and Ampere, which is another server provider based on ARM technology, and Fujitsu as the software vendor, are being tapped for next generation of the Open RAN in Vodafone networks. They got the slides last week. We knew this was coming, but we couldn't put it there. We didn't know the timing. Finally, the ARM advantage, compared to the standard of what is being deployed right now in the vRAN, what is there, and the technology that is there, depending on what level of acceleration or ARM support you do, you will get something like between 2 times to 4 times gain. Or if you translate this to power efficiency, power consumption, something between 50% or 75% saving the power. This depends if you are only losing the ARM accelerators, like inline accelerators, or you're also switching to the server, which is also a source of power consumption. So a little bit of review. Eventually ARM, we are here to represent our ecosystem. This is through the ecosystem it's that we are reaching to your homes. For the vRAN server silicon ecosystem, we have, of course, AWS, the Graviton 2s and 3s. AWS has been quite active in working and putting themselves up for being the infrastructure for operators. The biggest example has been Dish, that has been working with AWS since day one. We have Ampere. Ampere is a quite successful startup in California, quite new. They have commissioned ARM Neoverse cores and have built Ampere Ultra. These are chips that go from 64 cores to 180 cores, although the TDP or the power consumption of the chip is very similar to competition with 32 cores. Marvell, they have the chips Octeon 10 series that comes in different forms, a Fusion that is an accelerated acceleration chip. It includes some DSPs and Octane, which is a more pure DSP with still crypto accelerators, etc. And finally, NVIDIA's Grace superchip and Grace Hopper chips that are being positioned for more heavy loads, like the data center example we mentioned for the centralized RAN. When it comes to who's running these, who's making servers for these chips, which is what operators eventually care because they interface mostly with server vendors rather than operators. Ampere has quite a group of OEMs. Most famous ones are HPE and Supermicro that are bringing Ampere as a server. NVIDIA has also a group of vendors that have been commissioned as OEMs for the Grace superchip or Grace Hopper servers. Two of them are Supermicro and QCT, but more is coming. And finally, based on the Marvell chip, one of our partners, the Sina XG that we mentioned, has built an appliance. The terminology of appliance is that appliance is not a COT server. It's a purpose-built server. But usually appliance was referred to Nokia and Ericsson solutions that would come as a bundle. This is an open RAN appliance, means that it comes with benefits of an appliance, although you can run any software on that. It is still a vRAN, but it comes with the benefit of lower power consumption of that. It's a new product. We are exploring how the pickup from the operators will be about such a solution that is not a COT server by default, but do we really need the COT servers? That's the question that would be interesting to answer. Then the accelerator cards, the inline accelerator cards, that so much blood is being shed over it. We have, of course, accelerators from Nokia here, Qualcomm team, and Marvell. NVIDIA, NXP also has some accelerations. And finally, HQ, which is another startup based on California, they recently came up, targeting both small cell market and acceleration market. There is plenty of choice. Each one of these are targeting a special use case, a special mix of value that can be used for the acceleration of the vRAN. On the software ecosystem, we divide the players into two sections. There's the private network and carrier-grade network. For private network, there's many more options. It's a lower barrier to entry, of course, because of the level of maturity is needed. But for looking mostly at the carrier grade, we have been working with CAS vendors, leading CAS vendors like Wind River and Red Hat, which are native on ARM now. NEC, Fujitsu, and Nokia are our leading software partners when it comes to layer 2, 3, and layer 1, of course. Use cases, the layer 1 usually comes from one of the acceleration cards that I mentioned. And eventually for core network, NEC is announced, but more discussions are ongoing on that front. Finally, or almost finally, we launched a lab called ARM 5G Solutions Lab almost more than 1 year ago. This is a lab that is being run in partnership with Tech Mahindra. We started this lab for a place for different players to come together, work, and test their solution, and finally demo that to the ecosystem. This is a lab that has been visited by many, many operators to see the strengths of ARM ecosystem there and show the value, benchmarks, maturity, and it has been quite well received. I'm not going to explain one by one, but many solutions in that lab that shows mixed match of various partners that we mentioned on various servers together. And the top 4 are what we have been seeing more for carrier-grade solutions, and some of the rest of them mostly are good for private networks and so far. And finally, what is clear of all this, we hope if you take one thing back home, is that the future definitely is on ARM. That is as clear as day. Okay, I went too far. Going back. Thank you.
All right, thank you, Mo. And we will move now to a panel discussion section. So I would like to invite to the stage our esteemed panelists. So Mo, if you can please take a seat. As you are kind of working with everybody, maybe you sit in the middle. Then Joel Brand from Marvell, Matt Conrad from Intel, Christian from NVIDIA, and Nenander from Sankhya Lab, or Tejas and Sankhya Lab. Excellent. And Vaifro, obviously, Dariol. Thanks for reminding me. Yeah, exactly. So let's start off with a kind of a simple question. So can you just explain from your point of view the needs that you see for computing in Open RAN, either from telco enterprise perspective, and maybe we'll start from Matt.
Oh, well, thank you for having me, Ole, firstly. And I guess Christina, I wasn't at the session this morning, but Christina told me to start with a hug. Joel, she told me to give you a big ass hug. So that's.
And I was told to make sure that to tell everyone that we are missing Christina.
Yes, good.
Yes,
we are, and so am I. So I mean, again, I think Christina mentioned it. I believe she did. In our hearts of hearts, Intel has seen what's happening in the data center. Hardware, software, disaggregation, and this has been our vision for RAN as well as core for all of telecom. Not only does hardware, software disaggregation allow programmability, as Vodafone mentioned they want, but it simplifies flexible software, creates flexible software, simpler to get software to market by disaggregating it, and it speeds up innovation on this. I mean, again, our vision here with hardware, software disaggregation is to get to a point where I'm doing 10 software loads a day for RAN. 10 a day. We're at 1 a quarter. If you have hardware, OS, and software together and you're testing it, you're never going to get there. Right? Where you need to separate the two, automate, simplify, then we can unleash the power that the hyperscalers have on AI for mobile broadband, automation to remove services. I mean, our vision is pretty clear. We've been true to this since day one. But I will say this. I'm so happy that everyone's on this stage. You know, the amount of investment in RAN hasn't been this high since maybe the 90s. So RAN is topical. So I'm welcoming all of you into this ecosystem. Competition will make all of us go faster. And I'd love to see AMD at this show, coming to market with silicon diversity for x86. So by design, in x86, we have supply diversity. So again, I think the future is laid out. Graphics, fintech, all other industries have been through this journey, and I'm just hopeful for telecom to follow the same path.
Thanks, Matt. Thank you. Maybe Christian will.
Right. So thank you for having me here. I definitely agree with one thing, what you just said, is that we look at the disaggregation between the hardware and the software. And this is something that Vaifro mentioned. It's very important not only to have the disaggregation, but also to have this fully software-defined infrastructure. What does it mean? That actually means that you want to go away as much as possible from dedicated accelerators. It might sound a bit controversial, but it doesn't mean we remove acceleration. Yeah. We don't want to remove acceleration. What we want to do, we want to bring in the acceleration where it's really needed, but also provide enough flexibility to make the infrastructure software defined. I think this is very important. Why? Because a lot of power savings, actually, when you look at the RAN infrastructure, comes from optimizing radio. And optimizing radio is a process. We have new standards, new capabilities. In the future, there will be AI being able to optimize utilization of the radio. And for that, all this, you need the infrastructure that is capable, future-proof, to implement quickly all the new technology capabilities without needing to replace the hardware, which is costly, which is expensive and time-consuming. Yeah. So this is very important. And the second reason is if you have fully software-defined infrastructure, you have the ability to run a multitude of workloads on the same infrastructure. What does it mean? That you have one infrastructure that enables you to being reused for different purposes, depending on whether there is AI workloads or whether there is more need for RAN. Yeah. And you save a lot of capex on that, but also opex because you increase the utilization of the platform. So I think that's the direction, but it also doesn't mean that you need something like this everywhere. Yeah. So that's why we see more in the direction of data centers, private enterprise networks, where actually you have a lot of compute, but there are many different solutions which maybe suit better different type of environments. So that's my 2 cents.
Thanks, Christian. Mo, do you want to have a quick comment? Obviously, you
sure.
talked about it.
I touched on that a bit when I was talking. Especially now that we are moving to massive MIMOs, and 64 by 64 is not the end of this. I'm pretty sure it will go up. More and more compute is needed. Definitely we need stronger chips. The question is what kind of balance you need for acceleration. The one difference that everybody is coming to realization is that telco loads, especially this layer 1, which is almost black magic, is very different from your traditional cloud. You can get away, if you are running a database, etc., a lot of cases you can get away with a pure CPU solution. But here, definitely, no matter which path you go, you need some level of acceleration. And finding the right balance of this is the key to be able to get to that software hardware disaggregation as much as to get as close as possible. It won't be completely possible because you shouldn't use any acceleration for that. But there is a sweet spot here on this balance that's the challenge of the industry.
Joel?
I think the question was, why do we need compute in the RAN?
Correct.
Right?
Correct.
That was the question. So that question implies that we do not have compute in the RAN, and we need it in the future. You need compute to run your toaster.
Yeah.
And every base station, every DU, every RU has enormous compute capacity, okay? And this compute capacity today, if you buy a system from Ericsson, it comes with mass production of CPUs. And if you buy a system from Nokia or Samsung, for example, it comes with ARM-based CPUs packaged in a Marvell chip. That's what you have today. You don't have to wait for the future. Also, if you want to run a DU on a chip, that's what you have today. Okay? If you open a DU, in many DUs you will find one chip, and in the absolute biggest DUs you'll find 2 chips. Okay? So that's the reality today. And if you're looking to add machine learning to these capabilities, you'll find that these capabilities exist inside the chips already. All this discussion about Cloud RAN and ORAN and all the reason we've got kind of the whole chip ecosystem here in front of you is because the operators are looking at the hyperscalers and they're saying, hey, they've done something right. They've figured out how to take advantage of IT improvements, of scalability improvements, of a different type of reliability architecture, and that's what they want to bring to the radio access network. And that's what all of us are trying to do as an industry, and these are the things that are truly changing in the industry. All this discussion about whether there is an accelerator this, an accelerator that, these things will not change meaningfully. But how we architect the systems, whether we are able to pull the DUs into a data center nearby and leverage traditional, or what the hyperscalers are using in order to scale servers and use multiple servers for redundancy. That's really the question. Can we do that? And to be honest, that has very little to do with whether there is an accelerator or not. It has a lot to do what is the latency between the radio and the data center, how far, what the distance is, do you have the fiber optics in place? These are the kind of questions that will eventually determine whether Cloud RAN has any future.
All right, thanks, Joel. Ninander, Maybe you could actually introduce in a few words also Sankhya Labs and maybe tell us for the audience and maybe explain what you do as well, and your thoughts obviously on the compute demands for.
Yeah, my name is Gnaninder. I head the sales and business development activities for Sankhya Labs, which is now part of Tejas Networks, a Tata Group company. We have been, looking at SDRs since a decade, and we've built wireless SDRs over a period of time, and successfully so. So there are three things that we believe that needs to be considered. One, given the heterogeneous nature of the RAN workload, I think we will need domain-specific architectures. One size fits all does not work, and we don't believe in it. Number two, virtualization of the L1 software, right? How do we, virtualize these accelerated functions and open it up through standard interfaces as a microservice, right? So people can actually, with this, what we term as hardware containerization, just like software containers, you can swap in and swap out, your new algorithms for people to come and test and, get it into the deployment. So how do we open up that interface so that enables diversity in the L1 software ecosystem? And number two, by virtualizing and creating a software layer, how do we ensure the DU software can be portable across platform architectures? I think that's been our focus, and that's where we are looking at. The third one is, when we are designing, architectures, how do we natively build observability so that, it enables two things. One, you can meter the resources, which means it can enable providing RAN as a service, right? Metering of resources, much like in the IT world, where you actually meter and you have the Kubernetes of the world, actually metering the resources. That's number one. Number two, it enables a closed loop system architecture where you can look at what your compute utilization is dynamically and adapt it to the environments that you are actually operating in. So these are three main areas where we believe would help this Open RAN ecosystem and really look at truly opening up the architecture. Today, through Open RAN, we have disaggregated horizontally, but we have not really looked at vertical disaggregation and the L1 disaggregation. And that's where we are, putting our efforts to come out with some technology innovations.
Thank you, and I'll actually come back to that soon. But before that, let's jump into the discussion we had this morning and actually go into the topic of how to do the acceleration. I think there's a less debate probably in this panel that some kind of acceleration for layer one is needed. I think it's probably more of a question how to do it and where that should be done. And maybe if I start with an operator here, that is the architecture, whether you do inline or look aside, more of a question what area you would probably like to optimize in your network, whether you're going highly distributed architecture or more of a cloud RAN centralized approach or something else.
Yeah, like like the operator here. I think that the question, this is more a question that we put forward to the vendors rather than answer. For us, is not really, it's a matter, but is the effect. For us, the matter is the total cost of ownership. And another important point is not to be tied with a solution. So whatever is the implementation chosen, we want to be able to disaggregate the system at the point that we can change the solution. Not that we have a problem, but they change the implementation without redoing all the software validation, without redoing all the software development. So operator will own more of the system, will have more responsibility. So we don't even know how much is the cost to maintain the software. So we want to minimize that part. That is the major risk for an operator when approaching ORAN in his complete disaggregation.
And maybe Matt, you want to comment from Intel perspective?
Yeah, and I only heard Christina's presentation secondhand, so
Yeah.
I just wanted to say that, something like FEC, forward error correction, turbo or LDPC and 4G and 5G respectively, no one's innovating in that layer, in that domain. It's fixed function. That is really what Intel has viewed as a candidate for acceleration. Yeah, things like layer 1, there's a tremendous amount of differentiation going on across vendors, lots of different implementations. So full layer 1 is not something that we are looking to create an acceleration of because people want to change it, people want to adapt it and compete. And again, I missed the conversation this morning, but the acceleration type in your architecture for RAN has kind of played out. You've got 3 big vendors, they've each picked their horse for the next 3 years.
Yeah.
Right? And there'll be another chance to change architectures in some future time. But the game is played out. The debate is over. Intel has had 3 implementations of what you call look-aside FEC. We started with FPGA. FPGA is not really hardware. It's RTL code. And by doing acceleration in FPGA, we blurred the hardware-software divisions. We had to ask HPE to deliver all RTL code, which didn't work out. Then we went back to Samsung, who is now playing around in hardware. So we abandoned an FPGA as an accelerator. Then we went to fixed function, a fixed ASIC for FEC in a PCIe form factor. Wasn't bad, a little bit better than FPGA, but it consumed power all the time. That's what happens in ARM, is you always consume power or some amount of it. And it also took up a slot. In RAN, we need every available slot for radio connectivity, for fan-out in the front end. So the third implementation of our FEC was to put it on die. We have a CPU. There was an area of the CPU that can take IP. We put our FEC IP on die. It's a low latency bus between the CPU and this area. Shared cache. Yeah, it's very power efficient. Only when you use it does it consume power. Very scalable. It simplifies the system, but more importantly, I now have more faceplate room for front-haul connectivity. So again, this is our 3rd generation. We've learned some hard lessons. We got things coming in the future too, but putting it on die, following a BBDev interface and defined in ORAN, it's an open interface. We can use an external accelerator. You can use the CPU for other workloads. It's x86. But we just happened to, our 3rd generation of FEC accelerator is on the CPU. Okay, and there may be some other advances in the future, but again, I said a lot there.
Yeah.
We're focusing on fixed function acceleration, massive MIMO FEC in particular. LDPC for massive MIMO is a great example of savings by doing that. And we're trying to simplify the system, drive down power consumption and cost. So thanks, I'll turn it over.
Thanks, Matt. Maybe Christian, you want to comment from a GPU perspective?
Definitely. So we are heavily involved in building acceleration on top of the GPU.
Yeah.
And this is not GPU alone. Of course, it's combination of the CPU and the GPU. And the reason for that, because we see that at the same time, when you can introduce a lot of performance coming from the parallelized processing, it's much higher level that actually you can achieve on the CPU alone. And at the same time, the biggest advantage, I would say, of the GPU plus CPU architecture is that you have great ecosystem, and the tools are, it's basically an architecture easy to program. You cannot do this with FPGA to the same extent as you can do it with GPU. Like you can program easily a game on the GPU. That's how easy you can upgrade the software or create a new version of software on the GPU plus CPU combination. Yeah. So I see that this is kind of the combination, like sweet spot from our perspective, but our perspective also includes other workloads, as I mentioned earlier. So our architecture is so flexible that you can move from RAN to some other workloads or split this depending on your needs. You can put RIC with AI features in the future running on the same chip and optimizing the radio processing, optimizing the radio transmission to the level that is not available on the specified hardware, ASIC hardware. So this is one thing, and the ecosystem is very important here. So building the partners that can easily program on the architecture. So I think that's good for enterprises that want to deploy quickly on this architecture, and also for telcos, because they know that they can rely on partners to upgrade the architecture much faster in the future.
Can I maybe ask a follow-up question on that particular point? So Vaifro was mentioning the TCO aspect. So I guess with your sweet spot, you are really referring to a situation where you actually have these other workloads and you make a full use of your basically platform.
Exactly. So even the latest keynote from ORAN, NTT Docomo, when they start deploying something in Japan, but Fujitsu presented something similar during MWC when they actually put the AI workloads like video analytic on the same case where there is a RAN and there is UPF for private network. So that's one of the examples. You can find more and more use cases. The more workload you have, like centralized RAN or enterprise networks for large enterprises, the more flexibility you also have to move those workloads, then upgrade them. So fully software defined really bring a lot of value here, I must say. And this is our vision. This is our direction. And it suits in many cases for enterprises, for big telcos, also for micro network, especially centralized RAN.
Thank you. And actually, I want to jump to Joel. Obviously, you have a different view to the Lucas side implementation, and you are highly in a highly optimized acceleration for L1. I guess today mostly at the PCIe type form factors and so on. Maybe you could talk about that one and why you have that architecture and how do you see that evolving?
So I think it's important to start with where the industry is today and look at what a DU chip look like. So a DU chip, if you open the chip, and sometimes it's a collection of chiplets, sometimes it's a monolithic chip that was all the pieces were assembled together on the same die. That doesn't really matter. But if you look at the chip has multiple subcomponents. It has general compute. We are using ARM cores, but it's general compute. It has DSPs, because in the wireless world, a lot of the computing algorithms lend themselves very well to a DSP environment. It's got machine learning core, because we're moving into an environment where some of these algorithms can improve capabilities of the current codecs. And it's got a set of accelerators. FEC is one of them, but we have more. We have more because a lot of the logic that has been defined in 3GPP is very mature, and you can implement it in hardware, and you achieve a lot of efficiencies out of it. This is what a DU chip, by the way, this is also kind of what an RU chip look like. This is it. And that thing, you can put it on a motherboard if you want. You can put it on a PCB inside an appliance. You can put it on a PCB that has a PCIe interface and stick it inside a server. You can use it in many different configurations, but that chip is essentially a DU chip. And in the case of this particular conversation, it means that the L1 is processed in the chip, and that makes it into an inline accelerator solution. But it's no different than what is deployed in today's appliance or tomorrow in servers. If you want to put it on the motherboard, you're basically going back to a more dedicated appliance solution. if you want to reuse the server for running other things, it's typically better to put it as a PCIe solution, because then you can use the server for other things. If you put the accelerator, which you can, just take the DU chip and put it as the motherboard, no problem. You can do that. Then you turned it into something that is very, very specific for the radio access.
All right. I think Matt wants to answer that. Do you want to?
Well, I mean, there's a lot of discussion about traditional or classic base stations up here. I mean, they're the best thing out there today. Virtualized is catching up. There's a lot going on globally on cloud native or virtualized RAN. Some people call it cloud RAN. The pace of innovation over the last 5 years that I've been here is astonishing. I mean, it's just what's going on is fantastic. The challenge to the operator community is you need to speed up your practice to ingest all this innovation. The pace of innovation is going to a software world. It's very quick. I just want a last comment here, and Christina was much more dynamic than me, but when we're responding to RFPs for new markets on Open RAN versus, we're not comparing technologies or architectures. We're competing on, cost, TCO, and we're competing against traditional RAN. We're competing across multiple RATs, 5G, 4G, 2G in Europe. We're not just bidding on the massive MIMO stuff that's cool. Yeah, it's all RATs. Yeah, it's TCO, power consumption plus cost. And lastly, it's, there's an ecosystem that's needed here. An ecosystem of one gets you very close to lock-in, like traditional base stations that we're trying to get away from. So again, I'm just trying to mention this as we are working towards open. These solutions are past architecture. We're now, bidding on contracts with certain vendors have their strategies, and very, very difficult to change architectures just because of a white paper. Yeah, it's not easy to do. Maybe in 3 years there's another round of this, but the inline versus look-aside estate was very 2022. I got to be honest with you.
Yeah.
I'm with Matt on that one.
Excellent. Very good. Mo, if you think about the enterprise market and maybe with the less MIMO processing and so on, I know you have run L1 and actual 5G networks just with the standard servers basically without acceleration. How do you see that from an ARM's perspective working for enterprise market?
So enterprise is a market with completely different requirements compared to the operators. For an operator, the biggest cost sometimes is the hardware, but in a private network, actually the biggest cost is services. Somebody that is going to come, install that in that factory, put the radios, etc. That's the biggest chunk. So the TCO equation is a bit different, and their asks are also different. Rarely an enterprise is asking for really high throughput, cutting edge performance. What they care is mostly a merger of multiple services on the same box, which gives them easier IT, because this goes into the IT part of the enterprise rather than being a separate one. It is something for their automation, for their video analytics, etc. In that front, whenever it's just, they prefer to keep it as simple as possible. It is possible in some cases to do this on CPU alone, because the workload is not heavy. You don't need necessarily to go to accelerators, and that makes their IT process simpler. But sometimes they are asking for, hey, I already have GPUs, for example, for my AI analytics. Then it becomes an interesting game for what Christian was mentioning here, that the same solution is servicing there. From our experience, the enterprise is looking a little bit for simplicity in the offering over there. Sometimes it goes to the software, but if it's much more high demanding, again, we go back to a similar version of what is being provided to the operators. That blueprint, like what Marvell was suggesting, applies over there too.
All right. Can we really separate the L1 software from the actual hardware? I think that's one of the big questions also on the acceleration architectures and different implementations. And maybe Jenander, you could have a stab of that one first, and then we'll go around.
Well, the questions, can we really decouple the software?
Correct, and have a portable
and
one
L1,
software.
right? Absolutely yes, absolutely yes. But the question is, how open do you want it to be? I mean, for a CPU, you have an instruction set architectures, right? Whereas for inline accelerations, it's a complete black box. Now, each of these L1 functions or accelerated functions, how willing are we to open it up and make it, much more flexible for people to implement L1 functions and bring in innovation, bring in new algorithms to further, optimize, your spectral efficiencies or whatever, especially around beamforming, channel estimations, FEX and things like that. So yes, it is possible, but the question is how willing are we to open it up?
Matt, do you want to?
Well, I think the answer is not only yes, but it's in practice. Verizon very public about their deployment with Samsung on a virtualized, full stack. They have massive MIMO, 200 megahertz of 64T, 64R, operating in New York City, probably one of the most dense markets in the world. So I think there is an example that answers your question. I would change the question: is separating layer 1 and layer 2 software, is that actually possible in a massive MIMO performant implementation that's as good as Ericsson's custom RAN? I mean, that question is still not complete. It's still waiting to be defined in ORAN, Working Group 6. It forces RAN vendors to share IP to get a performant implementation. Yeah. That's really what I want to see. I want to see that question answered. Can we create an open layer 1, layer 2, which you need for inline, in a multi-vendor standard-based environment? Is this going to be as good as traditional RAN? That's the question back to the team here that are working on full L1 SoCs.
Yeah. Vaifro, do you have any view from an operator Malaga perspective here?
Well, just to pick up on the Matt, we may still need even L3 when you are going to try to save energy on the RU. So that is a challenge, because a lot of power saving when you want to control your PA. Well, you may need also L3. So the separation is quite difficult. By the way, the answer, as I say, Matt, it must be yes. We need to separate. We want to push through Working Group 6 this idea of hardware description layer, in which we try to we will correlate the software from the hardware. I'm not going into details, but I think we have found a couple of friends here on this idea, and this is good. But yes, the answer is even if it's no, it must be yes.
Okay, Joel, I know you have maybe a different view on this one. So
the question again was, can we separate the L1 software from the underlying L1 hardware? Right?
Correct.
The answer is absolutely yes, we can. In fact, you can run machine learning on an Intel CPU, and you can run any of the Intel application, any application you want, on an NVIDIA machine learning GPU. You can, but you don't. You don't because it's inefficient. You can. But at the beginning, there was all this discussion about power efficiency and all kind of things, and so far I haven't met a single operator who is willing to compromise on power and cost and all these basic things that the CFO tends to look at. So can we separate? Of course we can. It's not a problem at all. It's easy, and Matt is right. There are demonstrations of this. But will it take off on a massive scale? Not anytime soon.
May I answer? Can I say
Yeah.
quickly? This is very quickly.
Sure.
If we just take base station practices that are defined in traditional RAN, we have a pretty good working engine. Yeah, the traditional RAN that's implemented today does RAN fairly well, pretty well. But what the hyperscaler community has taught us, what the cloud team taught us is we can do so much better as an industry. It took me 2 weeks on the job at Intel to realize we're doing telecom a disservice by not bringing cloud native software automation, AI to this industry. We're doing it a disservice. It works very well now, but we're hampered, we're limited by our current or past envision of radio access networks. So then you start talking to CFOs and CTOs about the promise of a flexible hardware software programmable solution that is you can automate and you can drive 10 updates a day, like that you can't do that today in RAN. So the future is what we need to talk about as an industry to telecom. We need to make this flexible, we need to automate it, we need to drive AI in for better mobile broadband. And RAN will be better at the end of the day than it is today. Back to
Hallelujah.
Maybe I would like to comment on that because
Please.
there were GPUs mentioned.
Yeah.
So definitely hyperscalers are learning very quickly
Yeah.
and they don't sleep. And they learn that actually software defined really gives you a huge benefit. And you can see deployments even today. That was even presented this week where actually NTT Docomo achieved 50% reduction, which fits perfectly in what Mo mentioned earlier in the beginning. 50% cost reduction versus their previous 5th generation or 5G RAN that they had before. So their achievement on the CPU plus GPU architecture, fully software defined. And why Telco want to do this? I tell you why. They want to be able to swiftly move workloads between different units in their infrastructure. If they overbook the amount of compute on one server, maybe there are some workloads that can be more centralized. They want to move CU closer to the centralized network. Maybe they have more capacity now at the edge. They want to move some workloads over there. And then when there is time to improve radio, there is new standard, there is new configuration. Maybe they want to be versatile. They want to move swiftly to new, more efficient way of deploying this. They don't want to send the workforce to replace the entire infrastructure just for the sake of minor improvement. But if it's only software, they can do it easily. They gain performance improvement for every minute update of the standard software that they have. So this is really huge potential there, and we see it coming. Yeah? And this is actually abstracted of the discussion we had earlier of inline acceleration and look-aside acceleration, or no dedicated acceleration accelerated at all, because what at least I personally see it's an evolution. So you had look-aside accelerator. Now we are going in inline acceleration there, man. And NVIDIA is moving toward a converged system in the future, like with ARM and the Hopper super chip, where actually you have fully software-defined platform that can run these RAN applications, but also other type of applications that help deploy for enterprises. So that's one.
And that's absolutely true. That's the direction, guys.
Yeah.
But that's what was just described is central, right? It's pulling all the DUs into a data center and leveraging servers to run different type of applications, including the radio access DU. Absolutely, that's the direction. In order to get there, we've got a long way to go that has nothing to do with the chips.
Agreed.
It has to do with, again, making sure that the proximity is such that latency is low enough, that fiber optics is available. Serious challenges, but that has nothing to do with the chips.
Yeah, I totally agree with that. I think that today the concept of centralized RAN, people use it even with traditional base stations, so it's nothing new. Why doesn't anybody create traditional base station implementations that are optimized for CRAN? It's because it's a very small fraction of the global deployment. You know, CRAN is limited by non-CPU, it's fiber, access to data centers. There are many non-chip things that's preventing putting all the basebands in one location. And you know, to have a completely separate implementation for one versus the other is not what any of the big RAN vendors are doing today. So last point here is to take a GPU, and I love the fact that it's programmable, so we're best friends here. Programmable infrastructure is great. Does it make sense to take a 200, 300 watt GPU and put it in a distributed RAN cell site? No, it's not going to meet the TCO comparison to traditional. A traditional base station baseband unit is less than 250 watts. Yeah. The bar is high when you get past architecture and you get into cost and power. The bar is high. You need to be better than custom to get scale. So I just highlight that.
Okay, I must agree that putting the 250 watts GPU doesn't make sense for distributed RAN.
Yeah.
But I don't see that the environment and the ecosystem will stay static. So the reason why we introduce Open RAN and software-defined abstracted architecture is because the world is changing. And it's changing toward flexibility of moving those workloads from the edge to the cloud. The division between DU and CU was also specified for that purpose.
Yeah.
And we see this for example, of Japan, South Korea, which are pioneering. They are trailblazers in the way to centralized RAN. But it doesn't mean that it won't happen eventually in other parts of the world. Why? Because the density of the population will grow. And it's not only about the population, it's also about the IoT ecosystem. There will be more devices connecting to the radio station, especially for enterprises. They will need more of units connecting, transmitting. The enterprises don't want to put the cable into their factories or large areas just to provide them network connectivity. They want to move to 5G. Yeah. 5G enables that. And now, when we look at this ecosystem, it's completely different than it used to be. So the change is there. That's why the potential also of those new solutions will become more and more prominent. That's what I believe.
Excellent, thank you. Mo, can you maybe continue?
I just wanted also to bring attention to something. It's quite easy to find the key and try to open all the doors. Telecom is a very different market. I am here as a silicon guy, but my background is telco. And everybody sometimes forgets that below the TCP/IP level, nothing of telco is similar to anything else. Telco is always famous that its researchers don't read paper of any other field, except maybe for applied physics or some photonic or electronic level. And it has spent 40 years building this bit by bit to the perfection. Nokia, Ericsson, Samsung spend every year billions on this. Virtualization is good, it will have its own benefit, but it has to come in the telco flavor. Assuming that I will, as Joel was mentioning, I will run everything on the virtualize and get the same performance, is something that it's like finding the key, that thing you will get everything. Or assuming that if I do virtualization, I'm opening up innovation. It's really hard to tune any of the layer 1 algorithms to the better than what it is. Some sections like FEC is already optimized, but the rest of them, if you want to do channel estimates, you want to channel equalization, beating telcos at their own game is a high bar. It's good for marketing, but reality of that is harder. So there is some value in virtualization, but it's not going to open up the whole world like it happened in the cloud movement. I just want to caution that. It's something that everybody is learning as market is developing, deploying more and more, that there isn't any golden door that we are going towards that. It will be incremental value.
Sorry, just point out that at the end of the day, it's always a piece of silicon that does the algorithm. So either is at the edge or either is centralized. The innovation that we can put in the chip is common to the old architecture. So the worry mode, there will be also an ARM processor on the cloud.
Quick comment. I think it's regarding the power consumption, right? CPU versus an ASIC. Where we stand or where we are working towards, and given the experience we have found the right balance between the performance of an ASIC from a power consumption perspective and at the same time have the programmability of the chipsets, right? That gives a lot of benefits in terms of power efficiency as well as the performance of the compute architecture.
I just have two very quick things.
Please.
Firstly, on R&D. Traditional based, again, ex-Ericsson, ex-Nortel, come from Telecom as well. But the R&D spend on silicon for base stations is very unique per RAN operator. So there's 5 guys that have 95% of the market. Each of them are spending, let's say on average, 50 million a year in silicon and such, and tools for ASICs. If you look at what's happening in a virtualized type RAN world, you know, it 10 to X plus the investment in silicon. If we tap into what the hyperscale and every other industry is using for silicon innovation, and let all the RAN vendors focus on software, putting their R&D in software innovation, we're going to get more out of the industry. So yeah, that was the first comment on R&D spend, but we're tapping into a much bigger silicon R&D spend in cloud. And I think this is, for me, it's no longer if it's going to happen, it's when. The virtualization of radio base stations, there's so many other industries that have gone through this transition before us, graphics. And like remote radio heads, there was a multi-year transition. There were ops realities. Each vendor had their own appetite for introducing technology. And that's what we're in the middle of. We're in the middle of a 10-year process where we're moving compute from appliance, single purpose, single vendor, to generic platform. Some people are a little faster than others, but this is unstoppable. Now, remote radio head and multi-vendor RAN, that's still playing out. Yeah, the open radio and mixing, matching radios and baseband, that's still playing out. But virtualized baseband, it seems to be unstoppable from my chair.
Okay.
And by the way, that's true, right? Things are going to the cloud. There's no question about it. Yeah. The hyperscalers today have obviously become the biggest spenders on silicon. But look where that silicon is going, where that development is going, and what kind of chips that they're developing. If you understand what the hyperscalers are doing in the silicon area, you will be able to deduct where the radio access is going as well. Today, if you look at Marvell, 40-some% of our annual revenue is coming from data center. That's by far our biggest market. Telecom is only about 20% of the revenue. So twice as much as telecom is coming from the data center, and it's growing much faster. And if you look at what the data center operators, the large hyperscalers, are doing, they're investing in a lot of accelerators. They're investing in a lot of compute capabilities. Guys, this is all programmable. Everything is a programmable device, whether it has a CPU or a GPU or a DPU. These are all programmable devices. And look at the hyperscalers, right? Look at the Nitro of Amazon. Look at the Graviton of Amazon. Look at the TPU of Google. These are all programmable devices that are designed to run scalable and unique, and the kind of workloads that the application, the data structure, and radio access is a very similar application.
If I might tap to that, because this
Please.
is also a very interesting point. So just to bring it up, yes, there are many dedicated accelerators, and they have their use. So as you mentioned, Graviton, as you mentioned, also TPU from GCP, they put a lot of effort to develop those, and they try to push it to the market. And what happened? Actually, enterprises come and ask them for the GPU. And why is that? Because actually when you are building an application, when enterprise wants to build a solution for their problems, they don't only look at the hardware, they look at the ecosystem and how easy to develop, how quickly that they can develop new solution, optimized for the use case, and that can be later adapted as their business develops. So this is something why even Google, even AWS have GPUs in their portfolio. They are selling them. They are sold out. It's hard to get the capacity on those GPUs because it's so easy to use them and to optimize them for the business. And I'm not saying that they don't use the TPU or their Graviton. They do. The question is, how much return will they get there, and if it's even profitable in the future, where actually the change of the ecosystem will be faster, there will be more development. As we can see, there used to be progress. I think, Vaifro, you mentioned this very well. There used to be progress, how much compute is being needed, and it's growing exponentially. So there is more and more compute being utilized by enterprises, by customers, and it's growing. So the market is evolving, it's changing, and we need the capability to adapt for this quicker and quicker.
Excellent, thanks. I think that's a good segue for kind of a final question I would like to ask. Vaifro here was calling for photonic processing and photonic computing in a way, and my question would be that what is your roadmap now when we move 5G and we go forward to 6G? I know some of you are already discussing 6G designs with some of your clients. What should we expect from a chipset point of view in the future? What is your kind of a, if not exact roadmap, but the high-level vision that you're working towards that? And maybe Joel, you could start.
So the industry is largely dependent on the capabilities of the different foundries. Intel, TSMC, Global Foundries, Samsung Foundry. We're dependent on them to produce the chip. And the technology that they're able to bring differentiates the capabilities that the chip can extract. So at the moment, 5 nanometer, which is what is available today for commercial production, that's where all the chips that are going into the latest systems are. There is active work to deliver the next generation in 3 nanometer. That's TSMC has made that available, and that's why TSMC is so successful at the moment. There is a plan to bring the 2 nanometer to production. It's not quite ready. That's obviously why the US is also investing all the CHIPS Act money in order to bring those foundries to the US to diversify the supply chain. Intel can talk about their foundry process. But the more options we have, the better price we can get from the foundry to produce the wafers. We can drive the cost efficiencies of this down. And at the moment, unfortunately, the competition in this market is limited. TSMC is leading the way in terms of process technology in the world today.
Maybe Mo, if you want to continue.
So 6G is a very sexy topic, but nobody knows what's inside it. So we are deciding on the use cases, what we are going to dreaming of doing there. Even 5G has not been deployed to its full potential. A little bit early to start intelligently talk about it, putting aside the marketing hat. But one thing is clear, that it will need more and more data processing. But nobody will want their mobile bill to go higher. More and more processing means stronger chips, more power, more expensive chips, if the process doesn't follow, as Joel was saying. And then this eventually will happen in your bills. Now everybody wants unlimited data, fast, super fast, at the same price. This is the challenge that we are trying to solve in our part, that how do we optimize more the ARM cores to run these even not known loads by projecting that what kind of niches they will be requiring most, and adapting our cores to that, enhancing it generation by generation, and keeping the low power that has brought us here, has brought us the whole smartphone market, and is giving us every day a bigger share of the server market, laptop market. The challenge is to progress on that front while keeping the power low and predict what software is going to need in 5 years.
All right. Vaifro, do you want to add on my question, or
Yeah, just to point it out, sorry, I will be would be a win for me if I convince one of them to look at the photonic by the end of the day. Just to answer Joel, photonic, you need 100 nanometer. So you don't need more or less, more precise than 100 nanometer. So actually, you have the possibility to produce in different continents. So it will be a sustainable chip production environment.
And Inder, how do you see the future from your side?
Well, I think there is enough compute out there, and photonics, in my view, it has some time, before it can get into the compute architectures.
Okay. And then Christian, Matt?
So the way NVIDIA envisioned the future is actually converging all the type of computing power acceleration as close as possible, but retaining the flexibility, software definedness, and as well as maintaining power efficiency, which is very important. That's why the technologies like photonics, maybe in the future, will dominate probably not the whole chip or whole solution, but some parts of this as a part of the acceleration. There are many aspects of the ORAN architecture that we didn't touch upon. So we were talking definitely about the radio, but we also need to talk about networking that comes with this. So you need to accelerate cybersecurity. You need to accelerate the workload of the company that is actually utilizing the infrastructure. And if you have the architecture that can do all this in the simple way and be easily deployed, that's definitely huge benefit. As you can see, for example, now you can see everyone has a smartphone, even smartwatches. It's a unified software, maybe not the most efficient one from the power perspective, because you can have a smartwatch living 3 days versus 3 months of the normal watch, but the capabilities in the fast-paced world that we have now are really immersive. So that's actually what drives the discussion. And just wanted to mention also there is photonics, there is also quantum mechanics. So quantum solutions start coming up right now. People are already building something that works to some extent, and there will be cybersecurity also with that direction. And we also work actively in that area. So it's a very interesting future that we foresee. And hopefully,
I'm waiting for the NVIDIA quantum chip for RAN. That's what I'm waiting for.
We have just quantum simulators already, so you can try.
So this lastly, I know you're out of time, but thank you for your time. But very quickly, Intel's on a path of following Moore's law for vRAN. We've had 3 generations of commercial at-scale virtualized RAN deployment. And each one of these generations to date, we've been able to double capacity. We do that by a better CPU, more cores, and instruction sets that manage the RAN application natively on the CPU. You don't need an R&D spend to get access to our roadmap. This is x86. This is generic processing that every industry is using. We're doing this anyway, regardless if somebody gives us a NRE bill to do it or not. Like, this is mainstream stuff. So that's it. Moore's law for vRAN is our roadmap.
Okay, I think we saw the slide about Moore's law already. And we have many slides actually showing how parallel processing on the GPU defies this law. I don't know if the same with x86 because I haven't seen those slides yet. So maybe in the future we'll see something new. Thank you.
But thank you so much. Thank you. Let's give it a good applause.